January 16th, 1943. Portland Harbor, Oregon. The morning air hung cold and still over the Swan Island shipyard, where the smell of salt water mixed with the acrid scent of fresh paint and cutting torches. The SS Schenectady sat at her fitting-out dock, a gleaming monument to American industrial power. She had been launched only days earlier, her massive hull still vibrating with the echo of the riveters' hammers and the hiss of welding arcs that had brought her into being. At 10:30 in the evening, the ship spoke. A sound like a rifle shot cracked across the water. Then another. Workers on the graveyard shift froze, their tools suspended in mid-air as the metallic reports multiplied into a chorus. The deck of the Schenectady began to move, not with the gentle roll of the sea, but with something far more terrible. Steel plates rippled as if the ship were drawing breath. Then, with a roar that shook the foundations of the dock itself, a fracture tore through the tanker from bow to stern. When the noise finally stopped, Schenectady was no longer whole. Her deck and side shells had fractured completely. Only the bottom plates held the two halves together, sagging like torn fabric over black water. She had not been torpedoed, she had not struck a mine. The ship had simply torn herself apart while sitting peacefully at dock. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. By dawn, investigators swarmed the wreckage like surgeons examining a patient who had died on the operating table. Naval architects crawled across twisted steel, measuring angles and taking samples. Maritime Commission officials stood in small groups, their faces grim as they reviewed preliminary reports. The fractures were smooth, almost surgical, as if some invisible blade had sliced through half an inch of ship-grade steel like it was paper. The questions came immediately. Bad welds, cheap steel, design flaws, sabotage. But none of these theories could explain what the inspectors were seeing. The welds themselves appeared sound. The steel met specifications. And Schenectady wasn't alone. In the waters off Alaska, the SS John P. Gaines had split in two during calm seas, her bow plunging into the freezing Pacific while her stern drifted toward shore. The T-2 tanker Manhattan had fractured so suddenly while entering New York Harbor that her crew abandoned ship, convinced they had been hit by a German torpedo. Between January and March of 1943 alone, approximately 20 ships reported catastrophic structural failures. By the end of the year, the number would climb to over 100. These were not enemy kills. They were suicides, ships tearing themselves apart from within. To understand the scale of the crisis, one had to understand what the Liberty ship represented in the winter of 1943. After Pearl Harbor, the United States faced a mathematics problem that bordered on the impossible. German U-boats were sinking Allied merchant ships faster than traditional shipyards could replace them. In 1942 alone, German submarines sent over 1,000 ships to the bottom of the Atlantic. Each one represented thousands of tons of food, fuel, ammunition, and equipment that would never reach Britain. Traditional shipbuilding methods took 8 to 12 months per vessel. The math was simple and terrifying. At that rate, America would lose the Battle of the Atlantic before a single soldier set foot in Europe. Enter Henry J. Kaiser, a West Coast industrialist who had never built a ship in his life. Kaiser's background was in dams and highways, massive civil engineering projects that required moving millions of tons of concrete and steel. When the Maritime Commission approached him in 1941 about building cargo ships, establishment shipbuilders laughed. What could a dam builder possibly know about naval architecture? Kaiser knew something more valuable than tradition. He understood mass production. "We'll build them like cars," he told reporters in the spring of 1942, assembly lines on the water. The concept was revolutionary. Instead of constructing ships from keel to mast in a single location, Kaiser's yards would prefabricate entire sections in massive sheds, then assemble them like pieces of a giant puzzle. Hulls would be welded instead of riveted, saving thousands of man-hours. Women, many of whom had never held a welding torch before, would replace the skilled riveters who had gone to war. The work would continue 24 hours a day under floodlights that turned midnight into noon. By late 1942, Kaiser's Richmond and Portland shipyards were launching Liberty ships every 42 days. Propaganda films celebrated Wendy the Welder and Rosie the Riveter, symbols of American can-do spirit. One ship, the SS Robert E. Peary, was completed from keel to launch in 4 days, 15 hours, and 29 minutes. Newspapers called it a miracle. The world watched in amazement as American industry transformed warfare itself. But miracles, it turned out, had hidden costs. The first cracks appeared in the winter of 1942 to 1943, when Liberty ships began operating in the North Atlantic. Sailors reported hearing strange sounds deep in the hull, pings and groans that seemed to echo through the steel like the sound of glass under strain. Some refused to sleep below deck, preferring to risk the freezing weather topside rather than be trapped if the hull gave way in the night. Their fears were not superstition. On November 24, 1943, the SS John P. Gaines departed Dutch Harbour in the Aleutian Islands bound for Seattle. The air temperature hovered near 0 degrees Celsius. The water was colder still. As a large swell washed over the port bow, the ship's hull emitted a sound like tearing fabric. Within seconds, a fracture raced from the deck down through the hull plating. The crack didn't follow the welds. It tore straight through the solid steel plate. The ship split completely in two. Her bow presumably sank immediately. The stern section drifted until it ran aground in Alaska. 10 men were lost. The pattern was unmistakable. Ships were failing in cold water. They were failing suddenly, with no warning. And the cracks, when investigators could study them, showed characteristics of brittle fracture, a type of failure that shouldn't have been possible with the ductile steel used in shipbuilding. By early 1944, the problem had grown from an engineering mystery to a national crisis. Nearly 1,500 instances of significant brittle fractures had been documented across the Liberty ship and T2 tanker fleets. 19 vessels had broken completely in half. 3 had simply vanished at sea, leaving only oil slicks and floating debris to mark where they had been. The press began calling it the mystery of the breaking ships. Congressional committees demanded answers. In Washington, fingers pointed in every direction. Naval architects blamed the shipyard workers. Union representatives blamed the steel mills. Steel manufacturers blamed the designers. And while they argued, more ships continued to crack open in the night. The miracle that was supposed to win the war was failing, and no one knew why. In Cambridge, England, a metallurgist named Constance Tipper received samples of steel plate from several failed Liberty ships. Dr. Tipper was one of the few women in her field, a researcher who had spent years studying how materials behave under stress. When she examined the Liberty ship's steel under her microscope and subjected it to impact testing, she discovered something that overturned decades of engineering assumptions. The steel was fine when warm. The welds were sound, but at temperatures below a critical threshold, somewhere around 0 degrees Celsius, the steel's behavior changed completely. It transitioned from ductile to brittle. At room temperature, the steel could bend and flex, absorbing enormous amounts of energy before failing. But in the frigid waters of the North Atlantic, that same steel became as fragile as glass. Tipper's discovery explained the physics of the failures, but it revealed an even deeper problem. In a riveted ship, if a crack started, it would run until it hit a joint between plates. The overlapping plates would stop the fracture, containing the damage. But Liberty ships were welded. The entire hull was essentially one continuous sheet of steel. When a crack started, nothing stopped it. It could race from bow to stern in seconds, splitting the ship like an axe through timber. The welding that made the ships fast to build was making them fatally vulnerable. The solution seemed obvious: go back to riveting. But that wasn't possible. America didn't have enough skilled riveters. The war couldn't wait for ships that took 8 months to build. The Liberty ship program had to continue, which meant engineers had to find a way to make welded hulls safe in cold water. The first attempts focused on improving welding technique and steel quality. Kaiser's yards instituted stricter quality control. the Maritime Commission developed new steel specifications with better low-temperature toughness. These measures helped, but they didn't solve the fundamental problem. Even perfect welds in better steel couldn't change the basic physics. A continuous welded hull had no natural crack arresters. Then someone proposed what many engineers considered a radical, even foolish idea. If the problem was that cracks ran unchecked through welded hulls, why not deliberately introduce discontinuities? Install riveted seams at strategic locations, running the length of the hull. These seams would act like fire breaks, stopping any crack that tried to propagate through the ship. The proposal was controversial. Mixing riveting and welding violated every principle of modern shipbuilding. It seemed like admitting defeat, a step backward into obsolete construction methods. Some designers argued it would weaken the hull structure. Others worried about the time and labor cost of installing thousands of rivets on ships that were supposed to be built in weeks, not months. But the ships kept splitting. After the brutal winter of 1943 to 1944, when casualty rates spiked to nearly 2 catastrophic failures per 100 ship years of service, the Maritime Commission authorized emergency modifications. Starting in mid-1944, Liberty ships would be retrofitted with a minimum of 4 riveted seams running longitudinally along the deck and hull. These crack arresters, as they came to be called, would be installed on all new ships and added to existing vessels during routine maintenance. Additionally, designers rounded off the square corners of cargo hatches, where stress concentrations had nucleated many cracks. They installed gunwale bars, heavy reinforcing straps riveted to the deck edge. Each modification added weight and construction time. Each one contradicted the speed above all philosophy that had created the Liberty ship. But the data from ships at sea made the case that engineering theory could not refute. The results were immediate and dramatic. Ships fitted with crack arresters returned from the North Atlantic with surface cracks, sometimes dozens of them. But the cracks stopped at the riveted seams. The fractures that had once raced unchecked from bow to stern now halted within feet of where they started. The Class 1 failure rate, catastrophic fractures that rendered ships total losses, dropped from 1.9 per 100 ship years to 0.5. No ship fitted with gunwale bars ever suffered a complete structural failure at sea. By mid-1945, as the war in Europe ended, over 2,000 Liberty ships had been modified with crack arresters. The emergency shipbuilding program had produced 2,710 vessels, an average of 3 ships every 2 days for 4 years. It remained the largest shipbuilding program in history, and while the early failures had been spectacular and deadly, the ultimate success rate was remarkable. More than 2,400 Liberty ships survived the war. The ships that made it through carried more than just cargo. They carried the hard-won knowledge that would transform structural engineering. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. In the decades after the war, as engineers studied the Liberty ship failures in detail, they developed an entirely new field of study: fracture mechanics. The question was no longer just, how strong is this material, but how will this material behave when it contains a crack? Because all materials contain cracks, the question is whether those cracks will grow catastrophically or arrest safely. The mathematics developed from studying Liberty ship fractures became foundational to modern structural design. Every bridge, every pressure vessel, every aircraft fuselage built after 1950 incorporated lessons learned from ships that split in the North Atlantic. The concept of crack arrest, once considered a backwards compromise, became standard practice in critical structures worldwide. When engineers designed the Trans-Alaska Pipeline in the 1970s, 800 miles of welded steel carrying hot oil through sub-zero temperatures, they relied on crack arrest principles developed from Liberty ship failures. When the Golden Gate Bridge underwent seismic retrofitting in the 1990s, the welding sequences followed patterns designed to prevent catastrophic fracture propagation. Even nuclear reactor pressure, vessels, which must contain both extreme heat and radiation, incorporate crack arrest features descended directly from the riveted seams installed on emergency cargo ships in 1944. The solution that seemed like admitting defeat, mixing riveting and welding, installing deliberate discontinuities in structures designed for continuity, turned out to be the key insight. Strength doesn't always come from rigidity. Sometimes it comes from knowing where and how to be flexible, from understanding that the perfect can be the enemy of the good, from recognizing that the best structure is not the one that never cracks, but the one that can contain cracks when they inevitably appear. The women and men who welded Liberty ships never knew they were conducting the largest materials science experiment in history. Wendy the Welder, celebrated in propaganda posters as a symbol of American industrial might, had no idea that her work would lead to fundamental discoveries about how steel behaves at the atomic level when stressed beyond its limits. Constance Tipper, the Cambridge metallurgist whose research explained why the ships were failing, received little recognition during her lifetime. Her name rarely appeared in the historical accounts of the Liberty ship program. When she died in 1995, most obituaries failed to mention her wartime work. Yet every modern steel specification for cold service applications, every impact toughness requirement in shipbuilding codes, traces its lineage to her laboratory findings. The riveted crack arresters themselves represented a kind of humility in engineering, an admission that the grand vision of all welded hulls had been incomplete. But that humility saved thousands of lives. The engineers who authorized those modifications, who were willing to compromise their elegant designs with what looked like patchwork fixes, displayed a kind of wisdom that transcends technical knowledge. They were willing to be wrong in order to be right. By 1945, as the last Liberty ships rolled off the production lines, the lessons had been learned and codified. The American Welding Society published new structural welding codes. The American Society for Testing and Materials developed impact test requirements for steel used in critical applications. Ship classification societies updated their rules to require crack arrest features in all welded structures. None of these documents mentioned the SS Schenectady specifically. None of them told the story of the John P. Gaines splitting in two off the Aleutian coast, or the sailors who refused to sleep below deck because they could hear their ships groaning in the night. But every specification, every requirement, every design rule carried the ghost of those failures. The Victory ships that followed the Liberty design incorporated everything learned from 3 years of catastrophic failures. Their steel had better impact, toughness, their hatches had rounded corners, their hulls included multiple crack arrest features. Not a single Victory ship suffered a catastrophic hull failure during the war. 531 Victory ships entered service between June 1944 and August 1945. They sailed through Arctic convoys to Murmansk, endured typhoons in the South China Sea, and delivered supplies to Normandy under enemy fire. Their hulls flexed and groaned and absorbed punishment that would have shattered a Liberty ship. But they did not break. When the war ended, the shipyards fell silent. The great cranes stood motionless against the California sky. The welding torches cooled. The workers who had built 700 ships in Richmond alone drifted back to their lives, mostly unnoticed and largely forgotten. Many of the Liberty ships themselves were scrapped. Some were sold to merchant fleets around the world and continued sailing for decades. A handful were preserved as museum ships, floating monuments to industrial achievement. When inspectors examined these survivors in the 1980s and 90s, they found the crack arresters still in place, the riveted seams that had stopped countless fractures from becoming catastrophic failures. Today, only 2 Liberty ships remain operational, both serving as museum vessels. Visitors walk their decks and marvel at the simplicity of the design, the economy of the construction. Most never notice the riveted seams running along the deck edge and through the hull. But those seams tell a story more important than any plaque or display. They tell the story of how America learned to build things fast and safe at the same time. How engineers learned that the best solution isn't always the most elegant one. How a crisis revealed fundamental truths about how materials behave under stress. And how the willingness to adapt, to admit mistakes, to incorporate compromise into grand designs can mean the difference between catastrophe and survival. The Liberty ships that split in two were not failures. They were teachers. Every one of their fractures provided data. Every catastrophic failure revealed something new about brittle fracture, stress concentration, and crack propagation. The ships that survived carried that knowledge forward into peacetime, where it would save countless lives in structures that had nothing to do with warfare. When you cross a modern steel bridge, you're trusting crack arrest principles developed from Liberty ship failures. When you fly in a commercial aircraft, you're protected by fracture mechanics derived from studying ships that split in the Atlantic. When workers construct an offshore oil platform or a nuclear containment vessel, they follow codes written in the language of lessons learned from 19 ships that broke in half without warning. The illegal weld of the title, the solution that seemed to violate every principle of modern shipbuilding, wasn't really a weld at all. It was the rivets, the old technology, deliberately introduced into structures designed to eliminate it. The crack arresters that engineers initially resisted installing because they seemed like admitting defeat. Those rivets saved approximately 2,400 ships, thousands of sailors, millions of tons of cargo. And perhaps most importantly, they saved the principle that guided every military and civilian structure built afterward: design for failure. Assume cracks will happen, build in ways to stop them. The men and women who implemented these solutions worked in obscurity. No monuments commemorate the engineer who first proposed mixing, riveting, and welding. No plaques honor the shipyard workers who installed 15,000 rivets on each retrofitted vessel. History remembers Henry Kaiser, the visionary who revolutionized shipbuilding, but it forgets the people who fixed his vision when it proved incomplete. Yet their legacy endures in ways more lasting than fame. Every time a structure contains a crack without catastrophic failure, they are vindicated. Every time an engineer designs for damage tolerance instead of perfect strength, they are honored. Every time someone chooses adaptation over stubbornness, compromise over purity, they are remembered. The Liberty ships taught the world that strength and flexibility are not opposites, that the best structures are not the ones that never crack, but the ones that can survive cracking, that admitting a flaw in your design and fixing it is not weakness, but wisdom. Somewhere in the Atlantic, fragments of the 19 Liberty ships that split completely in half rest on the ocean floor. Their steel has long since begun returning to iron oxide, reclaimed by the sea, but the knowledge purchased with their destruction remains, encoded in every structural code, embedded in every engineering curriculum, implicit in every decision to design for reality instead of ideal conditions. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.